We are currently working on the binary search tree, and you've got a BST tester 1 and a BST tester 2. And in the BST tester 2, you're doing things like counting the number of nodes, and you're also finding the max and the min. You're counting the number of levels. You're doing a find method. And if you do the reading, both online and then also in particular in the book, a lot of the book reading should be helpful for completing some of those tasks. The one method that is more challenging than the others is the delete, and so I want to spend a little bit of time talking about deletion of a tree node from a binary search tree. And there are 4 cases, so we're going to go through the four cases. I guess before we go through them with this diagram, I should mention that the first 3 should be relatively easy to deal with, and it's the last one, the number 4 that's on my list. That's the one that is a challenge. So that's the one you're really going to want to pay attention to. So if you're trying to delete an element in a binary search tree, and I have a binary search tree that is already set up here. It is a binary search tree, which means that if you were to traverse it in order, you would get the numbers in order. You could print them if you were doing a traversal in order, and all these numbers would print out from least to greatest. So in this binary search tree, if you want to delete a leaf, and that's the elements that are kind of underlined in blue here. The ones that are leaves are the ones that have a left and right tree node that are both null. So there's nothing underneath them. And we've got a lot of the leaves here are at this level, and if I numbered these, I guess it would be 0, 1, 2, 3. It would be at the 4th level, which is actually the 5th of the 6 levels that we have. But if we have this level, that's where most of my leaves are. And if you want to delete an element that is at a leaf, all you need to do is you need to find the parent, and you need to have the parent point to null. There's no true deletion here. You're just having the tree node that is the parent, the one above it, point to null, and then Java's garbage collection will take care of that. So for example, if we were trying to delete the number 51, well, first we would do a search, right? You might use the find method to find the 51, and as you were doing that, you would want to keep track of the parent as you went, and you'd say, okay, I found it. And now what you want to do is, instead of having this point to 51, point to a tree node that is holding the object 51, you would want this instead to point to null. So if you could just make that point to null instead. So you're just reassigning in this case it would be the right tree node. You're reassigning it to null, and then Java's garbage collection again would take care of that tree node. You don't have to do a true deletion. You're just having this tree node that's holding the object 48, you'd have it point, instead of the right value pointing to a tree node that holds the object 51, you just have that tree node be null. Okay, and that's true for any of these that are marked in blue. So I would have the object 61, right? There's a tree node here that has a right tree node that is pointing to the object, or has the object 70. If you just take this, and instead of the right pointing to this tree node that is valid, you have it point to null, and it takes care of it. So the leaf elements that's probably where you should start if you're still working on the deletion. You should try to delete the leaf elements, or the leaves, and if you can get that done, then you go on to the next one. Okay, so that's a leaf, and then 2 and 3 are closely related. 2 and 3 are very closely related. So if we're talking about 2 or we're talking about 3, and these are color coded with green and yellow, they have one node either left or right that is null, and then the other one is a valid one. So here I've underlined in green. This one just has a valid, the 96, the tree node that has the object 96, it has a valid left tree node but not a right, and 78 is similar. And then I've got lots of them, or several of them, that are in yellow where they have a valid right tree node, but then the left tree node is pointing to null. So what you do in this case, in both of these cases, either 2 or 3, is you take the parent, and let's start with the 96. So we'll start with 96 here, and let's say we want to delete the 96 element, so we no longer want that to be here. What you do in this case is you take the parent, so you take the tree node that is the parent, and you have it point, instead of to the right, pointing to the tree node that has the 96 in it, you would instead have it point to this tree node object. And what it essentially does is it kind of shrinks the tree, it pulls the tree value up, and then this is going to no longer be here. Again, you don't really have to do a true deletion. Java's garbage collection will take care of it. You just have the parent point to the one valid side, right, whether it's right or left. You have it point to the one valid side, and it'll effectively change that. Let me take care of that. Okay, similarly, here's the 78. So here for the 78, I would take its parent, and I would have it instead of pointing to the object that is the 78, I would have it point here to the object that has the 76, and it effectively eliminates that. So you just take the parent element, the parent tree node, and you have it point to whatever comes beneath it. Now remember, there's just one valid side. There's either a left tree node and no right, the right is null, or there's a valid right tree node and then the left is null. Let's take a look at one of the yellow elements. So here, whoops, I lost that color there. So the yellow elements. Here, let's take a look at the 18. So I would want the parent to point directly to this 23, right? And then that would just effectively eliminate the 18, and then I would still have a binary search tree. It's still in order. Let's see if we've got where's another one? Here's the 48. So I would take the parent, and I would have it point to the one valid tree node that is attached to it, and so that would eliminate that. Really not really a deletion, you're just having it kind of skip over to its child, and that will eliminate the value, the element, the node that has the object value, and it's still a binary search tree. It's still in order. Maybe one more. How about, let's see. Well, I guess how about the 61 we want to delete? So first we'd have to find it, and then we would have it point to the 70, and that would eliminate that, and you still have a binary search tree. Okay, so those are the first three cases. Again, the leaf, you just have the parent point to null. For 2 or 3, you just kind of skip over whatever the current node is to the one valid node that is beneath it. But then 4 is a little bit more challenging. So I've got several. How many do I have that are tree node that have kind of valid left and right? So the root is one of them, and then 2, 3, 4, 5. Looks like I've got 6 of them. And maybe let's look at the 42 in particular. No, actually, let's take a look at the 75. Let's take a look at the 75. So here it takes a little bit more work in order to do a deletion. And the first thing you have to do if you're trying to delete an element where the left and right tree nodes are valid, it's got 2 of them, is you must find the minimum value in the right subtree. And that's an important thing to know. You must find the minimum value in the right subtree. So if we're looking at the 75, you go to its right subtree, which is topped off here by 96, and then you go as far left as you can, and that's the 76. And then you take that value, in this case the 76, and then you replace the object value. So you're not changing the link here, you are actually putting this value here. And then you need to make sure that you delete the tree node that contained the 76 before. So you would have this point to null, right, instead of the 76. And now you've gotten rid of the 75. and you still have a binary search tree. So again, the steps are, if you're looking to delete something in category 4, tree node with non-null right and left tree nodes, you must find the minimum value in the right subtree, and then you take whatever that value, whatever the object value is there, you're going to take it and you're going to replace the object that you want to delete with that value, that minimum value in the right subtree, and then you must delete that value where you pulled from to do the replacement. Okay, let's get rid of that. Let's do another one. Let's take a look at the 29. So let's say we want to delete 29. So the first thing we do is we must find the minimum value in the right subtree. So the right subtree is the tree that has 42 at its top, at its root. And I find the minimum value, well, that's 35. So I'm going to replace this object value with a 35. My first step. And then I need to go about deleting this element, this tree node that contains the 35. And when you do this, it's always going to be one of the first three categories. So when we deleted the 75, it was a leaf. This time it falls into category 3, where there's only one valid right value. So what you would do is the 42 would point to the 38 to delete that element. And now the 35 is where the 29 was. There is no 35 here, right, because we are skipping over it, and we still have a binary search tree. It's still in order. All right, let's take a look at another example. This time let's take a look at what is in the root. So let's say we want to delete the 54. So we must find the minimum value in the right subtree. So the right subtree is topped by the 75, and the minimum value is 61. So we take 61, and we would put that here. All right, and what we want to do, remember, now we need to delete this tree node that contains the object value of 61, and it will always fall into one of the three categories, 1, 2, or 3, because it is a minimum value in the right subtree. Well, this was category 3 again, so I would have 75 point to 70, and that would go over that. And again, I've got a binary search tree. The binary search tree is in order. The root hasn't changed, the object hasn't changed, but the object it contains, the numerical value, is now 61. Okay, maybe one more. Let's see. How about the, we did 75, we did, how about the 42? Let's look at the 42. So for 42, it has a valid left and right, and so we find the minimum value in the right subtree. So the right subtree is just topped by this 48 here, and the minimum value is 48. So we replace this object value with 48. And then we need to delete this tree node that contains the integer value of 48. And again, it'll always fall into one of the first three categories. In this case, it's the third one. And so I would have this now point to the 51. And that would effectively eliminate this tree node that contains the object 48. And we have maintained the ordering of our binary search tree. We're good to go. All right. So a quick recap here. So if it's a leaf, you just have its parent point to null. If it's a tree node with a non-null left, a valid left tree node, but then the right tree node is null, or if the tree node has a valid right tree node and the left tree node is null, then what you'll do is you'll take the parent and you'll point to what follows it. Take the parent and point to what follows it. And then with number 4, this is the trickiest one. This is the one that is most challenging. If you want to delete an element that has a valid right and left tree node, you'll need to find the minimum value in the right subtree. So look back to your min method that you worked on earlier. Find the minimum value in the right subtree, and then you need to replace the value in the node where you're trying to do the deletion with that minimum value in the right subtree, and then you'll need to apply a deletion of the value that you pulled from, and it'll always be in category 1, 2, or 3. Okay, thanks, happy coding, and come and see me during tutorial if you need some help. Thanks.